And that's how I wound up in a Peruvian prison for 3.5 weeks. All right. Pretty wild story, right?
Yeah.
Cool. All right. Number 7. A, did you guys get 3? And B, did you get 6? Baller. On 8. Alpha, did you get 8? 8 Bravo should be 5. Okay. Yuck on number 9 and 10. They're just asking where are the intervals. You've cut it into however many pieces. You may have notated this differently. I see everybody making faces. How did you interpret this question?
Flat line.
A flat line. Let's take a look. So it says partition, which we used that word yesterday, each interval into n subintervals, each of the same length. So for this one, there's a few different ways you can go. And Mickey, just so you know, because I saw that your answer was written differently, but I'm good with your answer. If you can tell me how wide each interval is, I think I'm fine with that. How did we work out the width of the intervals yesterday? Ooh, I don't think it was A plus B. I don't think it was A minus B either. B minus A, and then we divide it by n, the number of intervals that we want. So on this one, if you did B minus A over n, you got 1. Okay. Now, if you answered each one has a width of 1, I'm good with it. If you listed them all out, I'm good with it because they don't specify. If we partitioned this into 3 rectangles, it'd be 1 to 2, 2 to 3, and 3 to 4. If you told me the width was 1, I think that you could do the other part. If you didn't do the other part, I'm not going to count you wrong. I'm okay if you tell me the width. What's the width of this one? The width isn't 9. I'm not trying to trick you. I'm just pointing at it. 9 minus 0 over 9 is 1. So your first interval is 0 to 1, and then 1 to 2, 2 to 3, 3 to 4, so forth and so on. Number 11. How wide is each interval? Are you sure? 1/2? I think so. B minus A over n is 1/2. Cool. What would the first interval be, just to check? If each one is 1/2 wide. -1 to where? -0.5. And then -0.5 to 0, and 0 to 0.5, and so forth and so on. Okay, last one. How wide is each rectangle on number 12? 1/2 again. So -4 to 3.5, -3.5, I'm sorry, -3.5 to -3, so forth and so on, all the way up until the end. Okay, I'm A-okay if you did not write out all the intervals like this. If you tell me the width of it, I'm good with it. If you wrote them all out, I'm good with it. I assume that you probably checked the book if you wrote them all out, which makes sense. Like I post the answer key to you, you're good. Okay, is that as far as we went? Okay, anything we need to talk through? Angel, do me a favor. I want you to stand up, and I want you to spin that wheel with gusto. Okay. Do you guys want me to take it? And I'm not going to say whether I took this or not, and you guys aren't going to say whether I took this or not to your peers who are traveling. So it has landed on... So that's a mystery for the ages, whether I took that assignment or not. Let's keep kicking. Now, today, the language that we use to talk about math, it matters or not really? Like, if you don't know what all the language means, good luck doing the math, right? Like, there's a very clear connection between how comfortable you are with the language. Yesterday, we were looking at adding up some rectangles, and we were using which points to do so? We can use the left or the right. Now, for some functions, these are going to be the same, but other functions, we're going to introduce a little bit new language. As we look at these, if I were to take, and this is a good open-ended, not really, oh, there is an answer, so it's not open-ended, but I'm going to write a question up here in pink. I just want you guys to chat about it for like 60 seconds, and then we'll jump into the lesson. Will left sums always be, yesterday they were lower estimate or upper estimates? Lower, right? Will left sums always be lower estimates? Okay, if you have an answer in mind, I want you to be able to justify it as well. I'm going to give you guys like 60 seconds. You don't have to write this down. I could ask another question and say, will right sums always be overestimates, and so forth and so on. I'm going to give you guys 60 seconds. I just want to see what you come up with this idea. I already heard Sean answer it once, and you guys might all have. And that's okay if you have an answer, but I want the justification on top of it. 60 seconds, go. As we're looking at this, yes or no? What's the counterexample? If you have something that's negative, right? So if we look at this, and I'm just going to draw this one, and now I have this nice line here, all my left points are now overestimates, right? Everywhere, and I'm overestimating the area. What's different about this function compared to the one we did yesterday? Oh my, decreasing. Are there functions that change from increasing to decreasing? Yeah. So like if I said I want a lower sum here, you can't just always use left. Would you agree? Because if I want the lower or the smaller numbers, if I pick left points here, that works for that first one. Would it be a left point on this one though? No, if I want the lower estimate, it'd have to be that point all of a sudden, and I'd have to switch back and forth, right? We have a way to stick everything underneath the curve or above the curve, and maybe it's left and right isn't the right way to really truly talk about these. So we need a way to be able to discuss and get better estimates so that we can make sure that the estimate that we're getting is too low or too high, because we need to be able to say it's between these. So that's where we're jumping in today. Now, as we go through stuff, we are continuing on from yesterday, and we'll be here for a couple days. And there's going to be a few little statements that if you want me to write them, just let me know. What makes a better estimate of area? Like, what's better than using 3 rectangles? 4. And better than 4? 5. And ultimately, we're going to try to use how many? Eventually, it's going to become infinitely many. And there's some weird things that happen there if we think about it. If I have a distance of 1 on a number line, and I cut it into infinitely many small parts, what do you want to say, just your gut instinct, on what the width of each rectangle is? If I cut a length of 1 into infinitely many parts, each part would be how wide? Say that again. Something over 1. So I agree, but let's just check real quick. And this is just me thinking right now, just so you know, I should be pink. If I went from 0 to 1, could I put 1 cut in it? And each one is now half, right? Instead of making 2 partitions, could I do 3 cuts and make it 4 partitions? Each one is how wide? As I keep doing this, it's almost like there's a limit just waiting to happen. How wide is each one now? Ooh, I don't know how many there are. 1, 2, 3, 4, 5, 6, 7, 8. Can we just say it's 1/8? And then, is it getting smaller? If I let the number of partitions n, maybe, go to infinity, how wide is each rectangle going to be? One more time. 1 over infinity, which we know that number. 0. So there's this really awesome thing that's going to happen, because we just logically said that, wait a second, every rectangle is going to have a width of 0. And if a rectangle has a width of 0, does it really have an area? So maybe, just maybe, we have a way to start using these zeros and these infinitesimals, these really small things, to make the math work, even though it goes against our intuition. And that's exactly what we're building up to. So today, we're going to sneak in and we're going to get some formal definitions of stuff, and then we have some really important notation. Let me know when you want your curling break. Cool. Did we do curling in here yesterday? Okay, I have some news to share then. Good. All right, so check this out. Let's give ourselves a nice definition, and I just want to stay consistent. We're approximating the area. We're going to make this its own section now, and we'll say using partitions. Now, we defined this word yesterday, and I don't know if we formally defined it in our notes, but remind me, what's a partition? When it's split into parts. I'm good with that. So it's like I think about cutting a room into 2, or we can think about cutting the number line into however many pieces like we did on the homework last night. Now, we have a couple things that we are going to say with this. Using partitions, a couple statements. We will simply add rectangles. That's all we're doing. Now, eventually we'll learn how to add infinitely many of these. We'll simply add, and I'm going to say area or areas of rectangles. And that statement feels clunky when I wrote it. Just so you know, there's my shorthand for rectangle. Okay. Now, we will simply add areas of rectangles as long as, and there's a couple things that we need to be careful with these, and we'll make a few statements. So we're going to use partitions, we're going to cut intervals down, and we're going to make sense of it. So, 2 requirements. The first requirement that is needed to be able to do this nicely is we need the function f that we're trying to find the area beneath. It must be continuous. Which, give me a layperson's definition of continuous. I can draw it without doing something. Without lifting my pencil. That's a really informal way. Can you show me the really formal definition of what it means to have continuity? You will use your hands. Love it. Okay. Why is this not continuous? There's a gap. Now, even if I do this, there's still a gap, right? We need to make sure that when I use these from both sides, I'm really saying the what exists. Louder. The limit exists, and then when we do this, it's saying not only does the limit exist, but what's the point of pointing to our heads like this? So let's say that this is a limit as x approaches c, and it's 5. What point is my head right now? C, comma 5. I just make sure that it's defined right where that limit happens, and it works. That's continuity. Okay, beyond that, we're going to say on 2, for now at least, we'll require that f is non-negative. Not f in, f is non-negative. Why didn't I just say positive? 0. So we'll even be more specific. We'll say on some interval, some closed interval from a to b. So we have a function that is continuous and it either at the axis or above the axis for now. Okay, with this, we're going to really refine this. And you guys use this on your homework, so it's nothing new. To make partitions. And we're going to say to make n partitions on this interval. And when I say this interval, which interval are we talking about? A to B. Good. To make n partitions on this interval, we will create, and this gets kind of in the woods with vocab stuff, so let me know if there's anything unclear. We create subintervals. Now, this idea sounds ugly and stuff, and I'm not trying to psych you out, but it's way easier than you think it is, I assure you. If I have 0 to 1 as a big interval, can you give me a smaller interval in there? Like, instead of going from 0 all the way to n, if I use 2 equally sized intervals, it'd be 0 to where? And I'll draw this because it's hard to think this out. Let's say this is 0 to 1, and I want you to make this 2 intervals. I just put one partition right here, right? Now, each of them has a width of 1/2. So I have subintervals. My first subinterval goes from 0 to 0.5 because it's a smaller thing inside the bigger one. And the same, like it's like the homework problem that we did, just to make sure it's there. Okay, now the nice thing about these is that if we do this right, we'll say that we'll create subintervals of equal length. And I'm going to say equal length, but in parentheses, I don't want to think about it as a length necessarily. I'm going to think about it as a width. Because when we're thinking about the area, we use width or base times height. And I want to think about this little subinterval as the width of each rectangle. Now, to find this, and this is arguably one of the 3 most important things we're going to say today. And I'll tell you, it is. Not even arguably. It is. Okay. And we actually had this yesterday. Each interval's width will be on the x-axis or the y-axis if we're adding up rectangles? X-axis typically. And how do you say there's some change along the x-axis? Do we have a Greek letter that says there's a change in this? Oh my delta, capital delta. We're going to call the width of each subinterval delta x because it's a change in the x-axis. Now, you guys have already seen this, and I just want to see if we can make the connection. Mickey, you use this over and over and over on your homework, and we didn't define it yesterday. How do you find the width of each rectangle? Everybody? Mickey, for sure. I like the question you might not know off the top of your head, but I know that you do know it because I saw you do it. How do we find the width of each interval? You did b minus a, and you did what? B minus a over n. This is a really important idea. We will use b minus a over n. Now, when we look at these, is there anything completely brand new that we didn't see yesterday other than maybe a little additional language? I don't think so. I think we even had this. I don't know if we wrote this down or not, but we used it for sure. Now, where we're going to get into these. When we started class today, we looked at those problems from the homework and we said, hey, where are these partitions? Where are the areas? And then we started looking at that really open question, kind of open, I guess not even a little bit open because there was an answer, about whether we always get an over or underestimate, right? Okay. The snow's beautiful, is my guess. Fair. If we want to go get cold for a second, we can for a brain break. I'm fine with that. Curlers are cold all the time. Just throwing that out there. Okay, so let's use these. We're going to sneak in some new language. So nothing crazy here. We want a better way to ensure under and overestimates, and we want to be able to keep it straight. So we are going to be using, luckily for us, and we're not quite to being able to call them the right names, but we saw yesterday that we had left and right sums, and they do exist. If I want the left sum, or if I want the area using the left endpoints is how I would word that, I just pick the left endpoint of each subinterval. Everybody okay with that language? If I pick the right endpoints, I'm just picking the right endpoint of each little subinterval. And then we're just checking the function value there. Now, instead of those, we're going to add a bunch of stuff up, and these are going to look ugly for a second. We're going to sneak in 2 new words. We're going to give ourselves what is known, and this is a vocab, as the lower sum. Now, this sum, and if you want to be more formal, the real word is summation. I'm okay with just calling it a sum, just so you know. The lower summation. Now, notationally, there's very few times when I say you have to do it this way, but check it out. Notationally, you have to do it this way. When we talk about the lower sum, it is going to be a lowercase s. S sub n is how we're going to write this. Now, all that this does is it just simply tells me that these are rectangles. And we're going to add them up, and we'll get a mathy definition here in just a second, taken using the lowest point of each subinterval. I'm going to say the lowest end point, rather, of each subinterval. Now, we'll do some examples in this, and I'm sorry that I don't have a sheet of graphs for you, but we'll use essentially the same graph over and over. Now, when we add a bunch of stuff up, which is exactly what we're doing yesterday, is it crazy to add up 4 or 5 things? No, and it's realistically reasonable to ask you to write this plus this plus this and do it 5 times. Would it be as reasonable if I said, hey, I want you to add up these 1,000 things? Is it reasonable for me to ask you to write this plus this plus this 1,000 times? I don't think so either, which means we need a way to write this out. So the way that we indicate that we're adding a bunch of stuff up is S sub n equals, and when you think of me, probably 1 or 2 Greek letters comes to mind. Alpha, obviously. What's the other one? It's sigma, because how do we write a sigma? It looks like a what? It looks like an E. This lovely fancy symbol is the summation symbol. And just a reminder, you do not have to do it square and nice like this. Pretty common that people just use this. Notationally, I like the way this one looks. I actually don't love this one right now, so I'm going to fix it. But it's close to how I want it to look. Here is the summation. There we go. Okay, we are going to take the sum, and that's all this says. Add stuff up. And when we take these sums, we're going to use an index here. Last year we used n, I think, predominantly. We're going to switch it to I. So we're going to go from I equals 1 to n, and we're going to pause really quickly. Who recalls seeing this notation? Okay, so most people, not everybody, we'll do a practice with these, don't worry. But check it out. If I want to find the area of a rectangle, what do I need? I need the base and I need the height. Now, for these heights, what we're going to see is, I know that it's going to come from function f, right? Like, that's how we got the height of each rectangle. We did f of 0 or f of 1 or f of 2, whatever the case was. Now, I don't know what value we're at right now because it's going to change depending on the subinterval that we're working. If we want to use this, we can. We're going to say c for some value, and we'll call it c sub I. Notice the index just tells me where we're at. And I assure you this looks ugly, but it's so much easier than you think it is. This represents the height of our lovely triangle, or rectangle, sorry. This is the height at lower endpoint of, and this is going to get ugly for a second, the first interval would be the, like we would just say it's C sub 1. Does that seem reasonable? And if not, we'll get it cleared up. But all this index is telling me, this little I value, is which subinterval am I working in. And I think it's natural that we would start with the first and then we'd move to the second. So this is the lower endpoint of the ith interval, which is ugly for a second. And I have all the heights. And we're going to cycle through. What do I need to multiply, though, if I want the area? I have the height, and now I need the... One more time. The width. And up above, I'm not going to move my screen, but how do we say we find the width of each subinterval? B minus A over N is how we find it, and how do we write it? We called it what? Delta X. Now, for this, I'm just going to call this delta X, but I want you to know that eventually we're going to see some weirdness where we get delta X sub I. We will not deal with it yet because right now we're working with nice equally sized partitions. Okay, this is the lower sum. All that this is saying is find each little subinterval, find me the height, and add them up. We're using the lower point. If we have a lower sum, what else do you think we might get? The higher or upper sum. And I'm going to sneak this in as a vocab as well. And I'm going to let you guys use your powers of deduction and generalization. How do you think we're going to write the upper sum? Just letter-wise. Lowercase s was for the lower sum. You will not be wrong. And uppercase s, love it. So we'll say s sub n. Now, we'll make one other statement because there's one piece here that maybe not be clear. How would you define this? If the lower sum is a rectangle taken using the lowest endpoint of each subinterval, what's your thought here, Sean? Yeah, let's use same thing, rectangles, and I'm going to cheat because I can. I'm going to use the exact same language with the exception of one word. I'm going to use the highest endpoint of each interval. So I'll just make this really clear that this changed to highest. Exact same language, except now we get the big point in that interval. Okay. So we have this lovely definition, and you guys certainly take more time to write it because you can't cheat through it. Is this really going to change a lot? Are we still going to get the height of each rectangle just by taking f of c for some c value in that interval? Probably. Is our width still going to be delta x? Do we still have to add them up? And so we still do a sum here. So it's like the exact same thing with one small change as we're looking at it. So here we go. I'm going to just define this for us here, and then we'll have a single comment adding one thing to both of them here in just a moment. The way we write this is the upper sum, capital S sub n, is just the sum from I equals 1 to n of, and then here's the big change, and you might not even notice it, f of, what's different? Immediately. Subtle. Capital C because we're taking the upper sum. So we use an upper case. This is the what? What would this f of c sub I give us here? The height of the higher endpoint. That's like the height of our big rectangle. And then still we have all these heights and they must multiply by the what? Delta x, all the same. Now the only thing, and I'm trying to remember what it was. Yep, the only thing that hasn't been addressed here, and we might need the comment, what's n? It's not just delta x, it's not just the partitions, but you're close. So b minus a over n is how we get the width, right? And n just tells me the number of what? The number of partitions, or how many little subintervals we have, where if that isn't super clear, we'll just make that note. N equals the number of subintervals, or partitions if you'd rather. Okay. Looks super ugly, looks super nice. I didn't make this up, so you're not going to hurt my feelings. It kind of looks ugly. That's fair. I'll tell you, it's no different than what we did yesterday. None, except now we get some ugly notation. Okay, let's get some practice with these. And we're going to do 3 problems with the same. And we might even do more than 3. Here's what I want us to do. I want us, for the following example, and if we need a quick brain break before, I'm open to it, but we're going to get this problem listed first. We want to find the sum, and I'll say sums because there's going to be a few part of them, and A, B, and C are just going to be different sums. To find, or find the sums, weird, here we go. F of x, and we'll say it's the function x squared, from x equals 0 to x equals 10, using n equals, how many partitions do we want? And I'm just going to put dot, 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 and this is where our problems will change. I lied. I'm going to make that n sit solid here. We'll work it out. How many partitions are we using from 0 to 10? There is not a right or wrong answer other than one is wrong. Fair. Not going to use 0 of them. 10, deal. Okay, so we are going to use 10 little subintervals is what we're doing here. So on our first one, we are going to find what? Lower, upper, thoughts? Lower. So I'm just going to say S sub n. Now, for these, we'll do one together just to show you that this is so much easier, and maybe n equals 10 is going to be kind of a big number, but we'll still make sense of it. We can divvy up the labor here. We can use our calculators to help us if we need. But check it out. If we're doing this, I need a few little pieces of information. First thing is, if we're doing 10 intervals, I need to know how wide each subinterval is. If only there was a way that we could find the width, delta x, of every rectangle. So b minus a over n, right? So that's 10 minus 0 over 10, which tells me each delta x is how wide? That's a good sign. That's an easy number to work with. Okay, would a graph, help, do you think? Now, it doesn't have to be perfect, but I do think it would help. Anything else that, and we're going to actually graph this here. And just so you know, we are going to do another one here in a minute. I'm not going to graph this hardcore. I'm just going to graph it like this. Does that look like x squared to you? Like, I don't have the scale worked out. Okay, here's what we need to be able to do. And we're going to work out a nice way to do this here in a minute. But if we're looking, if we want the lower points, where is my first subinterval going to start? And I'm just going to pretend like we can go to 10. I'm only going to do the first couple. I didn't go all the way to 10. What's the lowest point of the function in this first subinterval? Fern claims 0. Does everybody agree that from here, and do you want a nicer graph of x squared? Do we need a nicer graph of x squared? Okay. Fern claims 0. Do you guys agree? Because if I check this is the lowest point there, okay, deal. So we'll just make that note. We'll say C sub 1 equals 0. Okay, how many subintervals are we going to have? I'm going to have 10 of them. So we won't have to write out all of them every time, but we're going to write the first couple. What's the next C sub 1 that we're going to plug into this lovely summation? So here's my first low point. That's my first interval. Here's my rectangle. It has no area. The next one If I have to choose between one of these endpoints, am I going to use the left or the right to be the lower endpoint? The left, and the rectangle would look like this, right? And it would be underneath. What is this endpoint that we're going to use here, which we would call C sub 2? C sub 2 is 1. And we keep going all the way up until ... we get to eventually C sub 10. And what's the endpoint of C sub 10? The very last one over here. Let's say that's 9 to 10. And there's my rectangle. Here's 9 and 10. And I know it's not really there. But what's the last endpoint? Is it 10? Why isn't it 10? Because that would be the, instead of right or left, which you are correct, it is the right sum. But I would use, that'd be the what instead? The upper sum. So looking at this, we have all these values and we've sorted them out to see this. Let's actually write out the sum then. We're trying to add the sum, lower sum, S, sub what number? How many intervals? Somebody said it. Good. S sub 10. So let's write these things out. This is the sum from I equals 1 to how far? To 10 of, and we'll write this out for now, f of c sub I times delta x. Okay, before we continue, if you've never seen this notation of the sum, which is the summation is the real way you say this, it looks ugly. It is so much nicer than we think it might be. This time, and this time only, we will be expanding it and making sure that everybody's comfortable with it. Okay, if I wanted to expand this sum, and entirely up, like if you were totally comfortable with it, you can just follow along, but I don't know that we did enough summations last year for everybody to be super comfortable with this. My index starts where? So from I equals 1, that's our starting point, which means if we expanded this, anywhere there's an I, I'm just going to plug in where we're at. So my first rectangle would be f of c sub 1 times delta x. That's the very first rectangle. Have I lost anybody here? Here in a minute, we'll plug in the number. That was a height of 0 because we plug in f of c sub 1 is 0. It's f of 0 times delta x. And then our index just starts jumping. And what's nice about this index I down here is it doesn't jump wonkily. That just jumps by the natural numbers. If I'm at 1 on the first one, where might I be on the second one? So this would be f of c sub 2 times what again? Because that's the height of that second rectangle. Delta x plus f of, we'll do one more here, and then we'll do some lovely ellipses. What's the next height? C sub 3. And we just start cycling through, right? Times delta x. And then I'm going to say plus, what do these ellipses represent? Everything that I'm skipping. What's the last one that I'm going to do? F of c sub 10 times delta x. Now, there's something awesome that happens with this. First off, there's some terrible things that happen because there's a lot of writing that we're going to have to do for this. But is there any possible way that I can make this expression simpler to look at, to work with, to deal with? What the F can I do? Louder, you're ready. I can factor this. What factors out of every single one of these? Delta x. So essentially what we're being asked to do then is I'm going to put the delta x on the right side when I factor it out because it feels more natural for me to have the delta x there. But what would be left inside then? We would have f of c sub 1 plus f of c sub 2. And I'm going to use my ellipses here, plus ... all the way to f of c sub 10. And then every single one of these just gets multiplied by what? Delta x. I don't care, honestly, if you put it on the left or right. I'm only putting it on the right because it's where it shows up here. Now, here's where our calculators, and honestly, probably our heads, are going to be able to do this. We don't need calculators. I'm going to change it. If I wanted to use all these, and I'm not going to use them all, because I don't think we need to really truly write them all, but this is really f of what? What's c sub 1? Our first endpoint we're going to choose. 0. Plus, what's f of c sub 2? So, and I'm going to put all these in. You said it's 1. I agree. And the next one is f of c sub 3, which is what? 2. And we just start kicking through here. Okay. I'm going to use the ellipses plus dot, dot, dot. And I'm just going to close it here. And then we multiply by, what was our delta x? 1. So that's pretty convenient. Now, this is kind of ugly. I hate that I have the bracket and the parenthesis. There we go. Now it's not going to be ugly anymore. Anybody uncomfortable with where we're at right now? So we're going to crowdsource, and I think we can all do this. What's our function f of x that we're working with? X squared. So you guys are going to help me out here. Just win our heads. I'm just going to have you guys give me these values. What's f of 0? Because 0 squared is 0, right? Plus, what's f of 1? Because 1 squared is 1. What's f of 2? 4. And the next one? And I'm thinking ahead. I know that the last point is at 9, right? So I have to go up to 81. So we're just going to add all the squares until we get to 81. What's the next one? Plus 25 plus. And I'm going to quit saying that. How about you guys just give me the numbers? Bet. And that's the last one we needed, right? And all of these f of values that we're adding up all get multiplied by what again? 1. So all we have to do, and we picked 10, maybe there's a nicer number. Somebody with a calculator or not, add up these numbers. I don't know what they are either, just so you know. I bet it's 285. We have a very gender split approach to this, which I find kind of interesting. Ladies, I just want you to know your idea is better. I think it's 285. Is it 285 or 385? Okay, so 285. What did we really just find? What is 285? The area under the curve. Awesome. So if we want to really just make sure that we have that area under the curve, I don't know the units. We'll just call them units for now. What's the unit on area? Squared. Now, if I wanted to do this with a different function or use the upper sum, what changes? So I'll give it a second because there's clearly maybe a little bit of confusion or just lack of confidence, or it's not snowy anymore. 30 seconds. What changes if I calculate the upper sum instead? Is a good problem, and it works out. We can add it up. If we had to go much higher than 10, I would look and hope that we have a more convenient way to calculate these things. And we do, and we will. What I want us to do is not a problem that I have in here, but I want you as best you can to try to just roughly, we're going to do one more example where we're going to sketch the sum, not sketh, weird, sketch the sum for n equals, I don't know, let's do it more reasonable. Let's say 4 subintervals. Now, on each of these, we're going to do 4 examples here, and maybe we'll do 5 even. You are going to draw a graph, and we're going to try just our best to replicate the same graph over and over, and it's not going to be crazy, but let's take a look. I can copy mine. I know you guys can't. Okay. I want a graph that does something more interesting than x squared, or does something more interesting than 2x plus 1. I'm going to say we're working from A to B on this, and we're just going to make a wonderfully fun function for f of x. And let's say that it's this function. So I lied. I'm going to make it nicer. It's going to look like sine in here. Cool. There's our function. Okay. Now, I'm going to make that point really clear and that point really clear. And I'll use a little light drawing here just to separate it. We are looking for that area. Now, I'm going to use this same graph on all four of them, and I'm just going to move it down a skosh. For this one, all we're doing is sketching. We are not actually calculating anything out. For this first one, I want you guys to sketch for me, I don't know, left, right, upper, or lower. Left. I'm cool with that. For the first one, we're going to do the left sums. And all we're doing is sketching it. We're not calculating it. Now, if I wanted to make my subintervals be 4 total, if I do this right in the middle, I make 2 intervals, right? And then if I cut that in half again, now I get all 4 of them, I think. I want you to just simply sketch the rectangles. Now, I'm going to put all the examples up here, and I'm just going to use the same graph every time. I'm going to throw you one weird one. It's not going to be left, right, upper, lower. We're going to do the left sum on A. On B, I want you to do the upper sums. On C, I want you to do the lower sums. And then this one we haven't used yet, but I'm going to throw it out here for fun, just so we see that something does exist. I want you to try to make sense of what I mean when I say the midpoint sum. Before, and I know you guys are still writing stuff, do you want to work through one of these together with me, or do you just, perfect, I'm good with it. Which one? There's like, I don't think any of them are, I'm not going to do the midpoint one with you, but I'll do upper or lower. Okay, let's do upper. I'm fine with that. Okay, does everybody agree? And you don't have to draw on yours, but I'm going to look at B first. So you might need a minute. I'll wait until everybody has B and a graph at spot B ready to go, and we'll come back to it. Okay, for this, I have technology that you guys don't, so I get to benefit. Does everybody agree that this is my first subinterval? Okay, so there's 1, 2, 3, and 4 is where they are, and I can see them. Okay, on the upper sums, I need to take the endpoint that's highest. On this particular one, is it the left endpoint of our first subinterval or the right endpoint? It's the right endpoint, so I'm going to use an obnoxious color here, and you know what? I think I get a crayon if I want. Yep, I'm going to use the crayon. I think it's going to be awful. Okay, so check it out. My interval is here, and you guys said the upper endpoint? Does that give me an overestimate? For sure. This is my first C sub 1 if it's an upper endpoint. What about the second one? Do you think we're using the left or the right endpoint? The left is apparently on my graph. Is it guaranteed to be the left endpoint on your graph? No, on mine it is the left because this endpoint is higher up than this one. If your graph is slightly different, I would use the other endpoint. We're not sticking to left or right. We're simply sticking to the higher endpoint. This is that one. Does that give me another overestimate? It does. Third interval. Left endpoint or right endpoint? The left one. How do you know? Like, and it seems like a silly answer, but I want you to give it to me. It's higher. Yeah, 100%. It's the upper value. So there's that one. And the last one, left or right endpoint? The right endpoint, and it looks like this. Are we guaranteeing in this example that we get a way overestimate? Yeah, for sure. All of this is super overestimate. Now, we've only did 4 partitions or 3 partitions and 4 subintervals, but we see very clearly an overestimate. I want you to do the same thing for the left, the lower sums, and then I want you, we haven't talked about it, but I know that you guys know what midpoints are. I want you to try the midpoint sum as well. I'm going to give you guys a couple minutes head start, and then I'll start sketching them on the board also. We'll pick up right here tomorrow. I'm going to help you. I lied. We'll pick up here tomorrow. I want you to try the midpoint. Make of it what you think of it. That felt clunky. Goodbye.